All right, let's talk about a number that seems super simple on the outside, but wow, is it hiding a wild story. We're talking about mathematical stubbornness, some really clever tricks, and a geometric twist you won't see coming. This is the story of the MRB constant.
Okay, so let's just dive right in. To really get what the MRB constant is all about, we have to start with how it's defined. And it all kicks off with what looks like a pretty harmless infinite sum. And there it is. That's our guy. The MRB constant is just the final answer you get from this infinite series. That big E symbol, sigma, just means add them all up. And what are we adding? Well, for every whole number n, from 1 all the way to infinity, we calculate a term. Then we either add it or subtract it, back and forth, back and forth. The term itself is just n to the power of 1 over n, and then you subtract 1. Simple.
I mean, seriously, how hard could that be? We've got supercomputers, right? We should be able to just tell a program, hey, start adding these up and get as many digits as we want. Well, this is where our story gets really interesting.
The big problem, and honestly the reason this number is so cool, comes down to one thing. This series converges so incredibly slowly. In fact, it's one of the most ridiculously slow converging series that people have ever seriously studied.
To give you some perspective, let's look at another famously slow series, the one for the natural log of 2. Now, to get just 4 correct digits of that number, you need to add up about 10,000 terms, which is a lot. But for our MRB constant, you need to calculate and sum almost 150,000 terms just to get that 4th digit to stop changing. That's not just slow, that's an absolute computational nightmare.
So what's causing this massive mathematical traffic jam? Well, the villain of our story is this function right here, n to the power of 1 over n. It shoots up, peaks right around the number e, 2.718, and then it starts this very gradual crawl back down towards its final destination of 1. It's this sluggish, lazy approach to its limit that just poisons the entire series.
And this graph just shows you the chaos it creates. If you just naively start adding up the terms, the sum never settles down. It gets stuck, bouncing back and forth forever between 2 completely different numbers that are a full unit apart. The series literally cannot make up its mind.
So, how in the world do you calculate a number that behaves like this? You can't just throw more computer power at it. That won't work. The answer is to stop fighting this series head-on and instead to outsmart it with a seriously clever mathematical trick.
And this really gets to the heart of how mathematicians think. When you're stuck with a problem that's just a tangled mess, you don't just pull harder. No, you look for a way to transform the whole thing into a different problem, one you actually can solve. And that is exactly what happened here.
Here's how this beautiful trick works. First, mathematicians figured out exactly which part of the term was causing all the trouble. It was a behavior that looked a lot like the logarithm of n divided by n. Then they did something kind of brilliant. They just subtracted that annoying part right out of the series. This left them with a brand new series that behaves itself and converges much faster. But here's the key. They already knew the exact sum of all those little problem pieces they had taken out. So after they summed up their new, well-behaved series, they just added that known value back in, and boom, the correct final answer.
And the difference is just stunning. I mean, look at this. On the left, you've got the wild, bouncing chaos of the original brute force method, and on the right, that's the sum after the subtraction trick. It's smooth, it's fast, it's a beautiful, controlled dive right into the final answer. It's like going from shouting in a hurricane to having a nice, quiet conversation. But, that one trick was really just the beginning. It cracked open a door to a whole world of mathematical techniques designed to speed up or accelerate how series converge. Mathematicians now have this entire toolkit full of ways to tame these stubborn sums.
And it really is like a toolkit. You've got your basics, like the Euler transform. Think of that as your trusty hand wrench, a simple, elegant tool that reweights the terms to get better results. Then you've got something like Atkins' process, which is more like a torque multiplier, a clever little trick you use at the end to get that last boost of accuracy. And then you have the modern powerhouses, like the pad-A kernel. This is your power drill. It approximates the really nasty parts of the function with simple fractions, and that gives you a massive speed up.
So just how powerful are these tools? Well, get this. With these advanced methods, modern programs can calculate nearly 3,000 digits of the MRB constant by using just the first 1,000 terms of a transformed series.
Just think about that. We went from needing 150,000 terms for 4 digits to getting almost 3,000 digits from just 1,000 terms. It's an absolutely mind-boggling leap in efficiency.
Okay, so we figured out how to tame this stubborn number. But the story doesn't end there. It actually gets even cooler. Because it turns out the MRB constant isn't just some abstract number that pops out of a calculation. It has a real geometric meaning that is both beautiful and totally unexpected.
Here is the absolute key, that troublesome little term that was at the heart of our series, n to the power of 1 over n. It has a secret identity. It is the exact edge length of a hypercube in n dimensions whose volume is equal to that dimension, n.
Let's break that down. So for n equals 1, we have a one-dimensional cube, which is just a line of length 1. For n equals 2, we've got a square whose area is 2, so its edge length has to be the square root of 2. For n equals 3, a cube with a volume of 3 has an edge length of the cube root of 3. And this pattern just keeps going into 4 dimensions with a tesseract, 5 dimensions, and on and on and on, all the way to infinity.
So what the MRB series is actually doing is playing an infinite game. It's taking the edge length of that 2D square and subtracting the edge length of the 1D line. Then it adds the edge of the 3D cube. Then it subtracts the edge of the 4D tesseract. Forever. It's measuring the tiny final imbalance in this incredible trans-dimensional chain of shapes.
And this quote from the original manuscript just says it perfectly. The MRB constant represents the limiting residual after infinitely many such near cancellations. The edges of these hypercubes get closer and closer in length, but they never perfectly cancel each other out. The MRB constant is that tiny little bit left over at the very end.
And so there you have it. We started with this series that was an absolute beast to calculate, a truly stubborn number. But by using some really clever math, we not only figured out a way to compute it, but we also stumbled upon this profound and frankly beautiful story about the geometry of higher dimensions.
It really makes you wonder, right? What other questions that look simple on the surface are just sitting out there, waiting to show us some deep, hidden connection between parts of the universe we never thought were related? That, right there, is what makes this stuff so incredibly exciting.